When you look at a massive skyscraper, you naturally assume it's anchored to solid bedrock, right? You see the steel beams, the concrete pillars, and you just trust the foundation.
Right. Yeah, you assume someone poured the concrete.
Exactly. But in modern cosmology, some of the biggest load-bearing pillars holding up our understanding of the universe, they aren't made of concrete at all. They're just penciled into the blueprint.
Mm.
So today we're doing a deep dive into this fascinating book by Boris Kriger. It's called At the Edge of the Cosmos, Stephen Hawking and the Fate of the Universe. And our mission today is to basically build you a mental metal detector.
I like that.
Yeah, we want to help you separate the hard, measured scientific facts from the beautiful but completely invisible mathematical assumptions. We're going to learn how to read science like a true insider.
Which is so crucial because that invisible foundation, that's where mature scientific fields often get stuck.
Right. Yeah.
Boris Kriger makes this really compelling case that physics rarely hits a wall because of bad data. The data is usually excellent.
The telescopes work fine, right?
Exactly. They work great. And the math can be completely flawless. But if an entire field's foundation rests on an assumption that everyone simply forgot was an assumption, you end up building castles in the sky.
Okay, let's unpack this, because before we go touring the edge of the universe, we really need to understand how physicists actually build these theoretical structures.
Yeah.
And Boris Kriger gives us this great three-part analytical toolkit for dissecting basically any scientific claim. He breaks everything down into measured, declared, and derived quantities. So the first one, measure that, feels pretty straightforward to me.
It is, yeah. The bedrock. A measured quantity is something physically pinned down by an instrument at a specific moment in time.
Right.
So like the temperature of the cosmic microwave background, or the arrival time of a photon, or the mass of an electron.
So an actual thing you can touch or see or register.
Right. There is a physical tool at the end of the chain of inference that is recording a reality. If the universe were fundamentally different, that number would be different.
Okay, got it. Then you have the second category, which Boris Kriger calls declared. And this is where my mental metal detector starts buzzing loudly. A declared quantity is a choice made by the researcher.
Yes. And often a completely necessary choice, to be fair. You usually can't run a complex equation without making a declaration.
We mean like guessing.
Well, it might be choosing a specific equation of state, which is essentially a mathematical guess at how a gas behaves under extreme pressure, or maybe setting a prior probability in a statistical model.
Okay.
It's a parameter chosen to make the math work, but nothing in the raw measured data actually forced that specific choice.
Right, nothing forced it.
Yep.
And that leads to the third category, derived. A derived quantity is a conclusion that follows mathematically from the first two. But Boris Kriger insists on a golden rule here, which I love. A derived conclusion inherits the status of its weakest load-bearing component.
Yes, it adds no reality of its own.
So if I use flawless genius-level calculus, but it's based on a declared assumption, the result is still just a declaration.
Exactly.
It's that penciled-in wall on the blueprint. It looks great. It makes the floor plan flow perfectly, but you cannot lean on it.
You cannot. And the history of astronomy provides a phenomenal illustration of this trap.
Oh, the planet things, right?
Yes. Back in the 1840s, the French mathematician Urbain Le Verrier noticed that the planet Uranus was not moving the way Newton's laws of gravity predicted it should.
Right, it was wobbling or something.
Right. The measured data was clashing with the derived orbital path. So to balance the cosmic ledger, Le Verrier made a massive declaration. He assumed on paper there was a missing unseen mass pulling on Uranus.
He just penciled in a planet.
He did. He calculated exactly where this hypothetical planet should be, and he mailed the coordinates to an observatory in Berlin.
And this is the crazy part. The astronomer in Berlin, Johann Galli, he gets the letter, he points his telescope exactly where Le Verrier told him to, and he spots it immediately.
First night.
He measures it. It's the planet Neptune. Le Verrier basically conjured a planet into existence with math, and Galli turned that declaration into a measurement in a single night.
It was hailed as the ultimate triumph of theoretical physics. I mean, it was huge.
Okay.
But success breeds overconfidence. A decade later, Le Verrier noticed another problem. The orbit of Mercury was also misbehaving.
Okay.
Its point of closest approach to the sun was drifting faster than Newtonian physics allowed. So flushed with his victory over Neptune, Le Verrier used the exact same method.
He declared another planet.
He declared a new inner planet, named it Vulcan, computed its orbit, and told astronomers where to look.
And astronomers spent the next 40 years staring into the glare of the sun, literally burning their retinas trying to measure Vulcan.
Oh, yeah.
But it never materialized, because decades later, Einstein's general relativity proved that Mercury's orbit was drifting because the immense mass of the sun was warping spacetime itself.
Exactly.
Vulcan was a phantom declaration.
And Boris Kriger draws a direct parallel between Vulcan and the dark sector in modern cosmology.
Dark matter and dark energy.
Right. We hear constantly that 95% of the universe is made of dark matter and dark energy. But we have to recognize those are declared bookkeeping entries.
Right, really. They're declarations.
Yes. When galaxies rotate too fast for the visible mass to hold them together, we declare dark matter. When the universe's expansion accelerates inexplicably, we declare dark energy.
So they're just penciled in to make the math work.
They make the modern cosmic ledgers balance beautifully, but despite decades of searching with the most sensitive instruments on Earth, we have not measured them directly.
Wow.
They are playing the exact role of Vulcan. They're waiting to either be verified like Neptune or entirely dissolved by a new understanding of gravity.
Okay, so here's where it gets really interesting.
Yeah.
Boris Kriger takes this mental framework of measured, declared, and derived, and he turns it onto the most famous physicist of our era, Stephen Hawking.
Yes.
He shares this great story about wandering through a damp secondhand bookstall in London in the mid-90s and finding this yellowing copy of Hawking's A Brief History of Time.
Which was just a cultural phenomenon of a book.
Oh, massive.
It sold millions of copies, though. Boris Kriger rightly suspects a large percentage of those were purchased displayed on coffee tables and abandoned around Chapter 4 when the math gets overwhelming.
Guilty. I definitely didn't finish it. But Boris Kriger read it all the way through. And he focuses deeply on Hawking's vision of the early universe, specifically the no-boundary proposal.
Right.
Hawking presented a cosmos with no edge, no first moment, and no singularity where the laws of physics break down. Boris Kriger says he visualized this model as a jug or a shuttlecock.
A shuttlecock, yeah.
He had like a shape with a rounded bottom that flares open endlessly at the top.
And to achieve that beautifully rounded bottom, which eliminates the infinite reality breaking point of the Big Bang, Hawking used a very old mathematical trick called Wick rotation.
Right.
He essentially took the dimension of time and temporarily treated it as an imaginary space dimension.
Wait, hold on. Imaginary space dimension. My metal detector is going off.
Yeah.
How do you just rotate time? What is actually happening in the math there?
It is a brilliant mathematical maneuver. In the equations of relativity, time and space are woven together, but time has a negative sign in the math,
Okay.
which makes the geometry incredibly difficult to solve as you approach the Big Bang.
Because of the negative sign.
Right. So Wick rotation involves multiplying the time variable by the imaginary number, the square root of -1.
Oh, wow.
When you square that, the negative sign flips to positive. Suddenly on paper, time behaves exactly like a fourth spatial dimension.
So time just becomes space in the equation.
Yes.
Yeah.
You can solve the geometric integral, easily smooth out the infinite point into a sphere, kind of like the South Pole of the Earth, and then rotate back to real time.
So if I'm at the South Pole and you tell me to walk further south, I can't.
Right.
Not because I hit a physical wall, but because the concept of south just loses its meaning at that coordinate.
Exactly.
It is a stunningly elegant idea. But multiplying time by an imaginary number just to make the geometry easier to solve, I mean, that is a massive declaration.
Exactly the point Boris Kriger makes. Hawking was incredibly scrupulous as a scientist. He explicitly named it the no-boundary proposal.
Totally.
He knew it was a declared choice about how to perform an integral, not necessarily a physical description of reality. But as that idea was communicated over and over, amplified through millions of books and documentaries and magazine covers, the word proposal eroded.
This is something every listener experiences today, I think.
Mm-hmm.
You know, you think about the science headlines you scroll past on your phone. An article will confidently state scientists discover how the universe began when the actual research paper says a novel mathematical model suggests a possible framework.
Oh, all the time.
We're absorbing eroded declarations constantly.
And that erosion is what concerns Boris Kriger. It is not a takedown of Hawking. Boris Kriger explicitly states his immense respect for Hawking's theorems, which will stand for centuries.
Right. This isn't about Hawking being wrong.
No, the issue is structural blindness. When a brilliant declaration is repeated without its underlying conditions, the public and even subsequent generations of physicists, they begin to treat the no-boundary jug as a measured fact.
The conditional if just wears off.
Exactly. And once an assumption solidifies into unquestionable dogma, people stop looking for alternative answers to what actually happens at the extremes of the universe.
Okay, so if Hawking's smooth bottomless jug is a declaration that eroded into fact, it makes me wonder about the other extreme end of a star's life.
Black holes.
Yeah, black holes. We treat black holes' singularities as an absolute fact. So is the bottom of a black hole just another penciled-in wall?
Standard textbooks certainly treat it as concrete.
Yeah.
The accepted narrative is that when a massive star runs out of nuclear fuel, gravity takes over and it collapses. First, radiation pressure pushes back.
Okay.
When that fails, the electrons resist being crushed, creating a white dwarf. If the gravity is strong enough to overcome the electrons, the neutrons resist forming a neutron star.
Right. I remember this from astronomy class.
But beyond that, standard physics claims there is no force left in nature to resist. Gravity wins forever, crushing all that matter into a singularity, an infinitely dense, infinitely small point.
But according to Boris Kriger, that infinite crush relies on yet another declared assumption about how matter behaves.
Yes.
He argues the resistance doesn't stop at neutrons. He proposes an alternative called the K-limit. And what I really love about this is that he doesn't rely on some theoretical future theory of quantum gravity. He uses standard nuclear physics that particle accelerators measure every day.
Which is so refreshing. The K-limit represents a profound shift in how we view matter. Boris Kriger points out a widely accepted but poorly publicized fact about the proton.
Okay.
If you look at a proton which is made of 3 quarks, the actual physical mass of those quarks accounts for only about 2% of the proton's total mass.
Let me stop you there. 2%.
Yeah.
Are you saying that 98% of the mass of the atoms making up my body isn't physical stuff?
It is not stuff in the way we intuitively think of it, no. That 98% is the kinetic and vacuum energy of the strong nuclear force that binds the quarks together. Think of the proton as an incredibly tight, heavy bag. The quarks are inside, but almost all the weight comes from the extreme tension of the bag itself holding them in.
So what happens when a collapsing star exerts enough gravity to finally crush that bag?
At extreme densities, several times denser than an atomic nucleus, that confinement fails.
The bag pops.
The bag ruptures. The quarks are no longer bound into individual protons or neutrons. When that happens, the massive amount of confined vacuum energy is unleashed into the space of the collapsing core.
Oh, wow.
And here is where Einstein's general relativity steps in. Energy with the specific properties of a vacuum does not exert an attractive gravitational pull. It exerts a repulsive pressure.
Wait, pushes back.
It creates anti-gravity.
Okay, so the standard model says a black hole is this bottomless paper shredder that deletes reality into an infinite point. But Boris Kriger is saying that before you ever reach a singularity, the collapsing matter shatters, releases a flood of repulsive vacuum energy, and the collapse just stops.
Halts, yeah.
Gravity pushes in, vacuum energy pushes back, and everything halts at a finite, measurable density. No infinite singularity.
What's fascinating here is how this elegantly dissolved one of the most agonizing crises in modern theoretical physics, the information paradox.
Right. Because Hawking famously proved that black holes are not entirely black. They radiate energy slowly over trillions of years and eventually evaporate entirely.
Yes, Hawking radiation.
But if the star that formed the black hole was crushed into an infinite singularity and deleted and then the black hole evaporates, the universe has permanently lost the information of what made up that star, which violently breaks the core rules of quantum mechanics.
Physicists have been waging intellectual war over this paradox for over 30 years. It's a huge problem. But if you apply Boris Kriger's K-limit, the paradox completely vanishes.
Because it never hits infinity.
Exactly. If the matter halts at a finite density, nothing is ever crushed out of existence. The star that collapsed the information of the matter that fell in it is all still physically there.
It's just squished.
Very squished. Furthermore, because of the extreme gravitational time dilation deep inside that, well, time practically stops relative to the outside universe.
Wow.
Under this model, a black hole is not a shredder. It is a perfectly preserved archive of the early universe. The information is never destroyed. It is just temporarily inaccessible behind the event horizon.
That is a staggering reimagining of the cosmos.
Right.
It turns a tear in the fabric of reality into a locked time capsule. But if a declaration can become a false fact in theoretical physics, what happens when we bake those declarations into the actual machines we use to observe the world?
It gets dangerous.
Yeah. Boris Kriger points out this phenomenon of erosion isn't just a quirky problem for cosmologists arguing over chalkboards.
Mhm.
It causes literal blindness.
This is perhaps his most chilling point. It's illustrated perfectly in his case study 13, The Hole, that the software deleted.
The ozone hole.
Exactly. It takes us back to the 1980s, shifting from black holes to Earth's atmosphere.
Right, so a team from the British Antarctic Survey, led by Joe Farman, they were measuring atmospheric ozone from the ground in Antarctica. And they were using Dobson spectrophotometers, which are instruments essentially designed in the 1920s.
Very basic.
Cheap old manual equipment.
Yeah.
And with it, they discovered a catastrophic continent-sized depletion of ozone, the famous ozone hole.
Which was a massive shock to the scientific community.
Oh, I remember, yeah.
Because at that exact same time, NASA had been flying the Nimbus 7 satellite overhead, mapping the Earth's ozone layer with multi-million-dollar state-of-the-art sensors.
And NASA had not reported a single anomaly.
Nothing.
How does an advanced satellite entirely miss a hole the size of a continent?
Because of a declaration hard-coded into the satellite's automated processing software.
A penciled-in wall.
Exactly. The programmers had built a quality control algorithm based on a model of what ozone levels they believed were physically possible.
Oh, no.
So when the satellite sensors detected the dangerously low ozone readings over Antarctica, the algorithm consulted its declared model, decided such low numbers must be instrument errors, silently flagged them, and scrubbed them from the standard reports the NASA scientists were reading.
That is deeply unsettling.
Yeah.
The machine literally filtered out a global emergency because the data violated its assumptions.
It just deleted reality.
And the British team only found it because they were looking at raw, unfiltered numbers. When they saw absurdly low readings, they didn't have an algorithm telling them it was impossible.
Right.
They suspected their instrument. They brought down a replacement, verified the numbers, and published. NASA had to go back and dig through their flagged, discarded data archives just to confirm what the guys with the 1920s equipment found.
And if we map that onto today's world, it is a profound warning. Every automated filter, every algorithmic feed, every data cleaning script we rely on carries a built-in model of what the programmer declares to be normal.
Yeah.
Anything outside that model becomes entirely invisible to the user. We are constantly wearing lenses made of unverified declarations.
So how do we take the lenses off? I mean, how do we fight this kind of systemic blindness? Boris Kriger argues that every serious scientific theory must come with an instruction manual for its own destruction.
It has to be falsifiable.
It must be falsifiable. So how does he put his own sweeping theories to the test?
Well, Boris Kriger walks the walk here beautifully. A major part of his work involves a topological declaration. He questions the large-scale shape of the universe.
Okay.
What if space isn't just an endlessly expanding flat sheet or a simple expanding balloon? What if space wraps around on itself in complex ways? This concept dates back to Carl Schwarzschild in 1900, suggesting the universe might have a topology where moving far enough in one direction brings you back or connects you to another point entirely.
Kind of like a video game where if you fly off the right side of the screen, you immediately reappear on the left side.
Precisely. Now, if space wraps in the specific topological manner, Boris Kriger suggests there is a very clear, testable consequence.
Okay, what is it?
Giant cosmic structures observed on one side of the universe should have observable counterparts on the exact opposite side of the sky.
Oh, wow. Enter astronomer Alexia Lopez.
Yes?
In 2024, she discovered something called the Big Ring. It is an unimaginably massive structure of galaxies in the northern sky, roughly 1.3 billion light-years across. It is so enormous that it actively breaks our standard models of how structures should form in the universe.
It shouldn't exist according to standard models, but the Big Ring fits Boris Kriger's wrap topology model flawlessly.
Wow.
So Boris Kriger did exactly what a scientist should do. He calculated the specific coordinates where the Big Ring's topological counterpart must exist in the southern sky if his theory is correct.
He found the exact spot.
He wrote a data search script, bundled it with the coordinates, and sent it directly to the astronomers who discovered the Big Ring.
So what does this all mean? The ultimate falsifiable test of this grand cosmic framework doesn't require launching a new billion-dollar space telescope.
No.
It doesn't require decades of engineering. All it requires is someone taking one afternoon with a laptop to run a script against publicly available survey data. If the coordinates are empty, Boris Kriger's theory takes a fatal blow.
And this raises an important question. Why hasn't anyone run the script?
Yeah, why haven't they?
Because no one has. Boris Kriger notes that the scientific filter organically ignores inquiries that come from outside the established institutional queue.
That invisible algorithm again?
Exactly. Attention is the rarest commodity in science, usually allocated by proximity, seniority, or whatever topic is currently fashionable. A request to look for a null result coming from an independent researcher simply bounces off the filter.
It is maddening. He is practically begging the establishment to prove him wrong, using data they already have on their servers. Boris Kriger has this brilliant quote in the book, "Wreaths are for other professions."
That's a great line.
Yeah, the highest tribute you can pay to a scientist is a rigorous public disagreement where the losing conditions are specified in advance. He has laid his declarations on the table, pointed to the exact measurement that will destroy his work, and is just waiting for someone to look.
It is the ultimate display of scientific integrity. He has provided the blueprint, highlighted which walls are concrete and which are penciled in and handed over the sledgehammer.
We have covered an incredible landscape today. From Leverrier's phantom planet Vulcan to the erosion of Hawking's no-boundary jug to the K-limit halting the singularity to the NASA software that nearly blinded us to an ecological disaster.
It's a lot.
The vital takeaway for you, the listener, is to take Boris Kriger's three-part test and use it as a shield. Whenever you read a confident scientific headline, stop and ask, was this measured by an instrument? Was it declared by an assumption? Or was it derived from a mix of both? Find that weakest load-bearing component.
And once you start looking for those declarations, you will see them everywhere. In economics, in medicine, in the algorithms curating your newsfeed.
But before we let you go, we have to leave you with one final mind-bending implication of Boris Kriger's wrapped space concept that we haven't touched on yet.
Oh yeah, this is wild.
We talked about giant galaxy rings having topological clones on the other side of the sky. But think about what that means for light itself traveling through the cosmos.
Right, because if the universe truly wraps around on itself and photons can travel endlessly across those connections for billions of years without hitting an edge.
Is it possible that when we point the James Webb Space Telescope at a tiny, faint, ancient red galaxy at the very furthest edge of observable space, we are actually looking at light from our own Milky Way galaxy? Light that left our neighborhood billions of years ago wrapped entirely around the universe and is just now hitting our lenses.
It is mathematically entirely possible. When you look deep enough into the cosmic mirror, we might literally be looking at the back of our own cosmic head.
And suddenly, we are right back to staring at that architectural blueprint,
Yeah.
wondering which walls are actually holding up the universe and which ones we just penciled in ourselves. Keep looking at, keep asking the hard questions, and we'll see you on the next deep dive.